In this video, we're going to introduce triple integrals. So, let's say we have a function of three variables, say it's f of x, y, z. In some applications, we'll want to be able to compute what we refer to as the triple integral of the function. That'll be over a bounded three-dimensional region. We'll just denote that with E. Perhaps think of E as a solid that has a density at particular points that's given to us by the function f. And maybe we want to be able to compute the mass of the solid, which would require us to do this triple integral idea. So let's see if we can make this a little bit more precise. So like what we do for single integrals and double integrals, we're going to divide up the region E, or the solid E if you'd rather, into what we refer to as sub-boxes. So remember when we did single integrals, we were integrating over an interval, and we sliced up our interval into sub-intervals. When we did double integrals, we took our region and cut it up into sub-rectangles. In this case, we're going to have sub-boxes because we're in a three-dimensional figure now. So we're going to take a box B, and we're going to make sure that this box contains E. And the only reason we're going to do that is because we're going to slice up the individual sides, if you will, of the box. The X interval, the Y interval, the Z interval. And it's just a little bit easier to talk about slicing up those intervals rather than just trying to slice up as some sort of a solid that may not have flat surfaces on its outside. So, and then what we'll do is that if we have some points in B that aren't in E, we'll just define the function to be 0 at those points. We did something very, very similar when we did double integrals over general regions. Remember where we had some whatever shape of a region that we were doing our double integral over, we just took a rectangle around that and then just said if we're in the rectangle but not in the region, we're just going to define our function value to be 0 at those points so it doesn't add anything in our integration. So we're doing the exact same thing here, we're just extending it to 3 dimensions instead of 2. Alright, so like I mentioned before, we're going to take the interval from A to B, and we're going to cut it up into L subintervals. We'll cut the interval C to D up into M subintervals, and the interval from R to S into N subintervals. And we'll denote the widths of each of these as delta X, delta Y, and delta Z. All right. So we will, and then again, just like what we did for subintervals and rectangles in single and double integrals, we're going to pick a sample point in the sub box, and I'll denote it X sub I star, Y sub J star, Z sub K star. We're going to make sure that the X sub I star is in the ith subinterval for the X interval, likewise for the Y sub J star and the Z sub K star. All right, and again, we're using this as a sample point so it can represent any point in that box. We now form what we refer to as the triple Riemann sum. We'll take the function evaluated at the sample point and multiply it by what looks like this change in volume. So this delta V here is going to be just the product of the delta X, the delta Y, the delta Z. It'll be the volume of that little sub box. So we're taking the volume of that sub box and then multiplying it by the function. So again, going back to that density application example that I alluded to before, if I think of the function as giving me density, I would have to do, did I say that's density per unit volume? I would need to multiply it then by a volume to get a mass. So in this case, this function would be giving us an approximation of the density over the entire sub box, and then I would multiply it by the volume of the sub box to give me an approximation of the mass on that small piece of the solid. All right. So then just like what we did for single and double integrals, when we do the triple integral, we'll take a limit of this Riemann sum. Of course, this is a triple Riemann sum, so I've got to let the L, the M, and the N all go to infinity, so I'm doing a triple limit of a triple sum to get our triple integral. And then much like what we mentioned with, well, we certainly did back in Calc 1, where we did single integrals, and when we did double integrals, we don't hardly ever use the definition to calculate the integrals. We always use our fundamental theorem of calculus. when we do multiple integration, we always do that through an iterated integral, and Fubini's theorem that we've talked about for double integrals extends to triple integrals. So let's just do a couple of examples to show us how we can evaluate these triple integrals through iterated integrals. So let's say we want to do the triple integral of y dv, where our solid that we're integrating over will have the x's go from 0 to 3, the y's range from 0 to the x value that we're given, whatever that happens to be, and then the z's go between x minus y and x plus y. All right, so when we set this up, our z is given to us in between two functions of x and y. So it's easier to integrate with respect to z first, because I've already got that in between those two particular functions. So that'll be my innermost interval of integration here. And then once I've integrated with respect to the z, I notice my y's run between 0 and x. So that'll be my next level of integration for the dy. And then finally, my x is given to us between two numbers, so my x will be integrated from 0 to 3. Remember again, when we do these iterated integrals with respect to a variable, that reference to that variable has to go away when we integrate. So I wouldn't want to go with my y first from 0 to x and then try to do my z, because my z is written, the z bounds are in terms of y. So I can't integrate with respect to y first and then with respect to z without changing what the bounds would be. Just like what we talked about with double integrals. So the way we've described this solid is determining what order we're going to integrate with respect to in this case. And then now we do our integrals just like what we've done before. For double integrals, we'll do it piece by piece. Since we're integrating with respect to z on the inside, that y is a constant. So I'll have y times z for an antiderivative, plug in the endpoints. When we simplify, we should get 2y squared at that point. Now we're doing the antiderivative with respect to y. That's a 2/3 y cubed. Evaluate at the endpoints. We should now be integrating the function 2/3 x cubed from 0 to 3. And then we finish this off like we always do. Antiderivative is 1/6 x to the 4th. And then plug in our endpoints and we get 27 over 2. Let's do another one. Let's say we want to evaluate the triple integral of x dv, where the solid that we're integrating over is bounded by the paraboloid y equals x squared plus z squared, and the plane y equals 9, and let's just keep everything in the first octant in this case. So here's a graph of the solid. Here's my paraboloid y equals x squared plus z squared. So you can imagine this bowl, if you will, opening along the y-axis. And then the plane y equals 9 is just that plane that slices vertically down through y equal to 9 there, and it's parallel to the x-axis. We want the first octant, so even though I've graphed the whole solid, really we just want the piece where the x's and the y's and the z's are all positive. So that'll help us with our bounds later on. All right, notice that our y here is given to us as a function of x and z. So it'll be easier to integrate with respect to y first, because I don't want to have to change around my bounds if I don't have to. So since my y is bounded below by the x squared plus z squared and above by the 9, my y ranges from x squared plus z squared to 9. All right. When we do the intersection here, we notice that the intersection of the x squared plus z squared surface and the surface, or the plane, if you will, y equals 9, that's a circle, and it's centered at the origin, and it has a radius of 3. You can see that circle here. You can imagine looking straight down the y-axis, and you would see that circle, x squared plus z squared equals 9. So for the x and z bounds, we're going to use the fact that we see that circle. Everything, if we were to imagine smashing it down onto the xz plane, that would be the circles we would see. We can describe the circle in several different ways. Let's say I solve for z, and since we're in the first octant, I don't have to worry about the negative square root. So I have my z would be equal to the square root of 9 minus x squared. That would be the biggest that z could get. Since we're in the first octant, the lowest my z can get is 0. And then your x would go from 0 to 3 in that case. So now we have our bounds to set up our integral. So again, we said we're going to integrate with respect to y first, and then with respect to z, and then with respect to x, the way we have this set up. All right. Again, we're integrating with respect to y, and antiderivative is xy. plug in our endpoints. We have x times, we'll have a 9 for the y, and then an x squared plus z squared for the y. So I can think of x just times that quantity. Now, I could go ahead and do this integral as it's written, but I notice that I've got a piece of a circle here, and I've got an x squared plus z squared here, which is much easier to represent in polar coordinates. So since I've got this circle that would be in the first quadrant, then in the xz plane, I can use my polar coordinates to describe that region as 0 to 3 for r, 0 to pi over 2 for theta. And then I can plug in r cosine theta for x, and then r squared for the x squared plus z squared. And then again, remember when we replace the differential here, we get an extra factor of r that pops out, so the dz dx gets represented with r dr d theta. So now we're doing the integral from 0 to pi over 2, integral from 0 to 3, r cosine theta times 9 minus r squared times r dr d theta. Notice that it doesn't matter that we're in the xz plane versus the xy plane. We can still use polar coordinates to rewrite this integral in something that's a little bit easier to integrate. Also notice that our bounds here are constants, and our integrand can be written as function of r no thetas times function of theta no r's. So we can break apart the iterated integral as a product of two integrals, and then calculate each integral individually. This should be a 3r cubed. My apologies, that's a typo. I should have a 3r cubed minus a 1/5 r to the 5th here. And then I have a sine theta for my antiderivative there. And if you plug in all that stuff, you should get 162/5 as your final answer.